Hello and welcome to a video on the ratio test. Now before I explain what the ratio test is and how we will use the ratio test to determine if an infinite series converges or diverges, I just want to review a couple examples that may have come up in class. First, recall these two very important facts. That if the limit of a sequence is not zero, the corresponding infinite series diverges. That's very, very, very important. We will be using that fact quite a bit. And we will also be using this second fact quite a bit, that if the limit of a sequence of numbers is zero, that means that the corresponding infinite series could converge. It has the potential to converge. But we have to actually do more investigation to determine if the infinite series does in fact converge. So where people often make a logical error in sequences and series is when they have a sequence that converges to zero and then they automatically assume that the series converges, which is not always the case. Let's look at some examples. So here we have the series from n equals 0 to infinity of 1/2 to the n. Well, first, let's think about the sequence of numbers here. So a of n is the sequence 1/2 to the n. Now let's think about what's happening with these numbers if I were to just start writing out some of the numbers in the list. When n is 0, 1/2 to the 0 is 1. Then when n is 1, we would get a half. When n is 2, we would get a fourth. Then an eighth, and a 16th, and so on and so on. So there's my sequence of numbers. It seems like these numbers are getting progressively smaller, progressively closer to 0. And they definitely are. We have a geometric sequence here. This is a geometric sequence with a common ratio of 1/2. And the terms of the sequence are approaching 0. The limit as n goes to infinity of this sequence is 0. So that means that the corresponding infinite series, this guy up here, that could converge. It has sort of the potential to converge. So we need to sort of do some more investigation here. So we need to think about, what do we know about geometric sequences and series? Well, we know that when we have a geometric sequence and the ratio is less than 1, or rather the absolute value of the ratio is less than 1, then the corresponding infinite geometric series converges. So we've got r here equals 1/2, so this certainly satisfies that their common ratio is less than 1. So that's going to imply that this series does indeed converge. So therefore this series we know converges. And since the series is geometric, we can actually compute the infinite sum, because we know, to shorthand this, that the infinite sum is going to be the first term over 1 minus the common ratio. So in this case, the first term is 1 over 1 minus the common ratio is a half. So the infinite sum is going to be 2. So not only do we know that that series converges, but we know the value that the series converges to. So let's look at an example that's not geometric. So here we've got 1 over n factorial. Well, first things first, let's think about the sequence of numbers. 1 over n factorial. Because the first thing we want to ask ourselves is, what is the limit as n goes to infinity of this sequence? Because if this limit is any other value than 0, if this is any other real number other than 0, or if this limit is undefined, then the series automatically diverges, and we're done. We don't have to do too much work. But what's going on here is that n factorial is increasing very, very quickly as n gets large. And since that's in the denominator and the numerator here is 1, the constant value of 1, that means that the terms in our sequence are going to be shrinking very fast. They will be approaching 0. Let's write out a couple of these terms. Starting with the 0th term, because that's where the sum starts. So 0 factorial is 1. So we have 1 over 1 is 1. Oh, I'm getting ahead of myself. I don't want to think about the series yet. I just want to write out terms of the sequence. So 1 factorial is 1, so it'll be 1 over 1 again. And then 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 780, and so on and so on. So there's my sequence of numbers. The numbers are definitely getting very small very quickly, definitely approaching 0. So this corresponding infinite series has a chance to converge. Now, this series is not geometric, but let's look at the ratios here in terms of what do we multiply one term to produce the next term. So here, if I want to go from the 0th term to the first term, I would multiply by 1. But then to go from the first to the second term, I would multiply by a half. To go from the second to the third term, I would multiply by a third. To go from the third to the fourth term, I would multiply by a fourth, and so on and so on. So it seems like these ratios are decreasing. So what this is telling me is that the individual terms in the list, they are getting smaller sort of faster than a geometric sequence where r is a half. Like, in fact, if I look at each one of these terms and I compare them to sort of the terms in the previous sequence, it looks like all these terms are smaller. In the previous sequence and series, they both converged. So I've got a series here where most of the terms, maybe excluding this first one, are smaller than the terms of a series that I know converges. Let me write this out. So basically, here's what I want to have going on. I want to sort of compare here this series, the 1/2 to the n. I know that converges, and I know it equals 2. I'm going to start writing out a bunch of terms in the list. Yeah. Didn't mean to move that there. Got 1/8, 1/16, and so on and so on. Now I'm just going to re-index this other sum, so I start at n equals 1. I'm going to sort of pull out that first 1. So this is going to equal 1 plus this next infinite series. So really, I just want to compare. I just want to start this second infinite series here at 1 instead of 0. So because if this converges and I throw on that first term, which is just another 1, the 0th term rather, then that's still going to converge. Well, let me start writing out these terms. This is 1 plus a half plus a sixth plus a 24th plus 1/120. Now let's start to compare these terms. The first two terms here are the same. But then for all the rest of the pairs here, like 1/4 is bigger than 1/6. 1/8 is bigger than 1/24. 1/16 is bigger than 120th. So basically what's going on here is that the infinite series from 1 to infinity of 1/n factorial is smaller than the infinite series from 0 to infinity of 1/2 to the n. And if I know that that first infinite series converges, that means that this second infinite series must converge because it's smaller than the first. And then if I tack back on the 0th term there, then it's still going to converge. So this converges. So basically, we now need a more systematic way to determine if a series like the sum from n equals 0 to infinity of 1/n factorial converges in sort of a more systematic way, and that is the ratio test. So I've written out sort of the definition of the ratio test, and as the name implies, we are going to be looking at the ratio of terms in the sequence. And we're going to be sort of thinking about how close the sequence is to a geometric sequence that would produce a converging infinite series. Because we know that if the sequence is geometric and the absolute value of r is less than 1, that the corresponding geometric series will converge. So that's sort of like what the ratio test says. This says that if you look at the limit as n goes to infinity of the ratio of successive terms, if that's less than 1, what that is telling us is that while the sequence might not be geometric, if the ratios are leveling off at something less than 1, that means that in the long run it's going to be behaving like a geometric sequence that produces a converging geometric series. And then similarly, if the ratio of terms is settling at a value that's more than 1, that means that in the long run the sequence is going to be behaving like a geometric sequence that would produce a diverging infinite geometric series. So let's actually sort of work out the ratio test. So now let's use the ratio test to determine if the sum from n equals 0 to infinity of 1 over n factorial converges or diverges. We already know that this series converges, but we want to prove that this series converges, this time using the ratio test. So in order to perform the ratio test, I'm going to evaluate the limit as n goes to infinity of the absolute value of a of n plus 1 over a of n. I don't need the absolute value bars in this particular example because all of the terms are positive, so the absolute value bars would be redundant. So we're going to evaluate the limit as n goes to infinity of a of n plus 1 will be 1 over n plus 1 factorial. Over a of n, it's going to be 1 over n factorial. And now I'm just going to simplify the complex fraction. And I wind up with n factorial over n plus 1 factorial. The limit as n goes to infinity of that. Just hop to another line. And now, one thing that you're going to be doing a lot when dealing with factorials and performing the ratio test is you need to be sort of proficient at simplifying factorials. So n plus 1 factorial, that's really just n plus 1 times n factorial. Because n plus 1 factorial, I'll just write it out down here, down at the bottom, because n plus 1 factorial is n plus 1 times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. Like, that's what n plus 1 factorial is. But when you look at this, n times n minus 1 times n minus 2 times all the way down to 3 times 2 times 1, that is just n factorial. So sometimes it's an efficient way to simplify factorials is you can take out a factorial and write out the first couple of terms, and then write out the rest of the terms in terms of a smaller factorial. Now, why this is useful is because, now look at what I left myself with here. These n factorials cancel, and now this is easy to evaluate the limit because the limit as n goes to infinity of 1 over n plus 1 is just 0. And since this value, this limit as n goes to infinity of a of n plus 1 over a of n, since that is a real number that is less than 1, the absolute value that's less than 1, that tells me that the corresponding series converges by the ratio test. So I know that this infinite series from 0 to infinity of 1 over n factorial, that's going to converge by the ratio test. So let's look at an example of an infinite series where the ratio test will provide an inconclusive result. So let's try to determine if the sum from 1 to infinity of n plus 1 over n cubed plus 2, let's try to determine whether or not that series will converge or diverge, and let's use the ratio test. So again, if we're using the ratio test, we're going to evaluate the limit as n goes to infinity of a of n plus 1 over a of n. Again, I'm ditching the absolute value bars because all of the terms of the series are going to be positive here, so the absolute value bars are not necessary. So this is going to be the limit as n goes to infinity of a of n plus 1 is going to be n plus 2 over the quantity n plus 1 cubed plus 2, and that's going to be all over a of n, which is n plus 1 over n cubed plus 2. And again, let me just simplify this complex fraction. This will be n plus 2 times n cubed plus 2 all over n plus 1 cubed plus 2 times n plus 1. Now, this looks quite hideous, but if I look very carefully at what is going on here, is that the numerator here, if I were to multiply out all of these terms, I'm not going to, but if I did, I'd wind up with a quartic polynomial with a lead coefficient of 1. And in the denominator, the same thing. I'd wind up with a quartic polynomial with a lead coefficient of 1. So I essentially have a quartic function divided by another quartic function. They both have a lead coefficient of 1. So the end behavior asymptote is going to be y equals 1. So this limit of the ratio of successive terms is just going to be 1. So the ratio test does not give me any conclusion here. The ratio test does not say whether or not this particular series converges or diverges. So my conclusion here is that really I'm at the same place where I started at the beginning of the question. I wanted to determine in the start of the question whether or not this series converges or diverges, and the ratio test offers no information on that fact. So the ratio test, this sort of implies that the ratio test is inconclusive. Inconclusive. So we're going to need a different test to determine if this series converges or diverges. It turns out that this series does converge, but in order to determine that, we're going to need the limit comparison test, which we will learn in a previous lesson. So by the time we get to the end of this unit, the biggest challenge is going to be when you're presented with an infinite series and you're determining whether or not that series converges or diverges, you're going to have a whole battery of tests to choose from, and you want to learn appropriate problem-solving skills and techniques to choose the best test for the series at hand. So by the time we get to the end of the chapter, if you were to see a series like this, you'll know, oh, the ratio of two polynomials, oh, I probably shouldn't do ratio tests there. I usually get inconclusive when I do the ratio test in that situation, so I'm going to go for limit comparison test instead. So you'll sort of learn some problem-solving techniques along those lines. So I hope you enjoyed this video, and good luck.